In the previous lecture, we talked about different materials properties, okay, and two of them are resilience and toughness. Okay, so if you have, let's say, a plot of force and the elongation, for example, you can actually calculate the work done by simply obtaining the area under the curve, okay, or integrating f dx. If you have a stress strain plot, however, okay, due to the nature of the units of stress and strain, so strain is dimensionless and stress would have units of uh, pascals or megapascals or pounds per square inch, for example. Um, if you're going to take the area under the curve, which we have known if you have here a whole curve, okay, up to the area of plastic behavior, for example. That area under the curve is your toughness, all right? And it is expressed as work or energy per unit volume, okay? So ang ginawa lang, yung FBX dito, you divide it by the volume of a material, okay? Let's say that the material has a constant cross-section, so you have the area, and then you have a unit length of a material, okay? So the area and the length would result to your volume, okay? So if you calculate this area under the curve, the resulting unit would be the same as the unit of your stress. And that would be, in this example, megapascals. And megapascal or pascal or other units of pressure or stress, it's the same actually as unit of volume. Let's say pascal is the same as joules per cubic meters, okay? So if you have megapascal, it's equivalent to megajoules per cubic meter. So the energy imparted is the mechanical strain energy. Okay, so again, it's the area under the curve, right? If you have a Hookean material or a material exhibiting Hookean behavior, you can approximate this toughness or mechanical strain energy by using the maximum stress, okay, or the ultimate stress, okay, squared divided by 2 times the Young's modulus of the material. Again, this can be used if the material is Hookean. Okay. Or, of course, the more accurate way to calculate that is just use your numerical integration techniques to calculate this area under the curve. Okay. And here are some materials of biological relevance and their corresponding resilience. So resilience is, in this context, different from the resilience we have discussed. So remember, si resilience, yun yung area under the curve up to the yield stress. So let's say this is, for example, kunyari straight line yan. Okay? And this, there is some point here which we call yield stress. Okay? And that area up to the yield stress is considered the resilience. Pero yung ratio ng energy returned over the energy imparted to the material, okay, that is, we can call in this case coefficient of resilience, and it's expressed in percentages. And you can see that collagen and resilin, which is found in your wing hinges, are among the most resilient materials in nature. Okay. I have here an idealized data obtained from testing of steel. Okay, so we already plotted strain versus stress in this graph. Okay, and we want to calculate the following. Number one, the yield strength and the ultimate tensile strength. Number two, the modulus of resilience. And number three, the modulus of toughness. So how can we do that? First, to obtain the yield stress, okay, So all we have to do is find that point, which we call yield point. Okay, it's basically yung point kung saan it will start, you know, it will start behaving like a plastic, no? Or in other words, hindi na siya, yung point na hindi na siya, nag-uumpisa na siyang hindi maging elastic yung behavior. Okay? So that's the yield stress, or the yield point rather. So if this is the yield point, kasi the reason is why we call that the yield point kasi ito yung straight line. Okay? And beginning from here, hindi na siya nagiging linear yung relationship. So ito yung yield point. So the stress corresponding to that yield point is 500. Okay? So therefore, the yield stress is 500 megapascals. How about the ultimate tensile stress? So ultimate tensile stress is the stress corresponding to the maximum point in the stress strain curve. So in this case, that point here is this, okay? And the corresponding stress is 900 megapascals. Okay, how about the modulus of resilience? Okay. So the modulus of resilience is it should give you a unit for energy, okay? And megapascal is a unit of energy per unit volume. And we know that the modulus of resilience is this area under the curve. So yung, imagine this as a straight line, right? You can, up to this yield point, okay? Yung area na cover niya, which is quite small compared to the area of the whole region, okay? So imagine you have like a triangle there. Okay, so from the yield point, cross the, the horizontal axis, no? So I'm using my mouse, but that should be a straight line and it forms a triangle, okay? So that area, okay, should be the modulus of resilience. Okay, so how do we calculate that? First, you need to calculate the modulus of elasticity. Okay, so how do we compute that? So modulus of elasticity is simply the ratio or the slope rather of this line here. Okay? So yung line na yan, yung slope niyan ay yung Young's modulus E. Okay? So it begins at 0.00 and ends at the approximately the yield point. Okay? So rise over run lang yan. So that would be 500 over the strain at that point is, okay, around 0.0025. Therefore, the Young's modulus is 200,000 megapascal. So to calculate the resilience, you have to integrate from 0 to this point. Okay. So, and that is, of course, if you do this integration, it will result to this expression. Okay. Or you can obtain that using the area of the triangle formula, which is 1/2 base times height. So this is the base. So this is the height and this is the base. Diba yung height? Yung sigma y, yan yung yield stress. Diba? Ito yung yield point, ito yung yield stress. So yung height, therefore, is the sigma y. Yung strain sub y, ito yun. Yung base. So height times base. So you can do that. Or yung result ng integration dito is this. Okay? So sigma y is squared over 2e. And using that, so sigma y is again 500 megapascal squared, 2 times the Young's modulus we have calculated a while ago. And the result is 0.625 megapascal, which is equivalent to 0.625 megajoules per unit volume in cubic meters. Now, how about the modulus of darkness? Okay, which we can also call energy of breaking. Okay. Ito yung resilience kanina. But this whole thing here, okay, yung area yan, okay, kasama yung sa resilience kanina, okay, yan yung toughness. So you have to integrate from zero, therefore, no? From zero up to the breaking point. So, saan yung breaking point? Ito. Yung strain kung saan siya na-break. In other words, the last point or the point of fracture in your stress strain data. Okay? And if the material is Hookean, we can approximate that to be UTS squared divided by 2E. Okay? But since it looks like this data does not really represent a Hookean behavior, we can use Excel. Okay, you can use your integration technique. Okay, you can search for video tutorials how to use your Excel in order to do numerical integration or calculating the area under the curve. So using that, you will find that the area under the curve, which is equivalent to your toughness, is 61.6 megajoules per cubic meters. So nakita nyo kanina yung resilience 0.6 lang, but the toughness is 61.6. Okay. Okay, let's have another problem wherein we will use mechanical energy balance in order to calculate. Okay, in this case, it involves the material spider silk. Okay, so you have here, if you have seen the movie Spider-Man 2, okay, starring Tobey Maguire, and yung kalaban niya doon ay si Dr. Octopus, tama ba? Okay, doon sa yung pinakahuling sa climax, parang gano'n, no? Si Spider-Man, he attempted to stop a speeding passenger train consisting of 3 cars, no? Yung bagon, traveling at 130 kilometers per hour. Okay. So he shoots 20 threads of spider silk, 10 to the right and 10 to the left. And each thread is about 30 meters long. Assume that all 20 threads have exactly the same diameter. The question is, what is the minimum thread diameter that is needed to stop the train? And we know that the strength of spider silk is 350 megapascal. Ang ibig sabihin nun, if you have the stress strain curve for that material, yan yung ultimate tensile strength niya, 350 megapascal. And the mass of the train is 10,000 tons. Okay. Also, you're given the Young's modulus, which is 24 gigapascal. So how do we approach this problem? It's simply like this. You need to equate the kinetic energy to the mechanical strain energy or toughness. It's your mechanical energy balance. Okay? Yung tren, umaandar, so meron siyang kinetic energy. Kinetic energy na yon will be conserved, will be transferred to the spider silk threads. Okay? So whatever kinetic energy is lost by the train will be gained by the spider silk. So assuming there are no other energy factors in here, like potential energy, so walang ibang energy terms. So kinetic energy is 1/2 mass times velocity squared. We know that from your general physics? Well, the mechanical strain energy is approximately sigma max squared over 2e. Tama? So yun yung toughness approximately if we assume that the behavior is Hookean. Now, remember though that this formula here, yung 1/2 mv squared, okay, ang unit niyan, if we are going to use the metric system, okay, or SI, let's say, no, that the unit of this term is joules. Okay? But this formula here, remember, ang ibibigay niya sa'yo ay what? Mega Pascal. Okay, megapascal. Bakit megapascal? Kasi sigma max, megapascal. Squared, so megapascal squared. But si Young's modulus is also megapascal. So matitira megapascal. But remember, megapascal is the same as what? Mega joules. Okay? Per unit volume. Because Pascal is simply joules per cubic meters. So, paano natin palalabasin yung joules? In other words, dapat we have to multiply this term by the volume of the material. And if we are going to assume that each thread is cylindrical, so the volume of a cylinder is what? The cross-sectional area, right? Times the length of the thread. Okay, so pi over 4d squared is the cross-sectional area, and L is the length of the thread. In the problem, it's given as 30 meters. Tama ba? Okay, and again, remember from the problem that there are 20 threads. Okay. So simply, you can just substitute, no? Okay. Yung given. So M mass nung trend, 10,000 tons, and 1 ton is 1,000 kilograms. Velocity is given 130 kilometers per hour. Just convert that to meters per second. So we would like to have all units in metric system. Okay. Sigma max, all right? Okay, in terms of Pascal, so 350 megapascals is kasi siya. So 350 times 10 raised to 6 Pascal squared. 2 times PE, 24 times 10 raised to 9 kasi 24 gigapascal yan. 5 over 4, what are we looking at here is the minimum diameter ng thread. Okay, so D squared. 30 meters yung haba ng thread. Then there are 20 threads. So if you're going to solve for D, you will get D is equal to 2.33 meters. Napakalaki ng diameter na kailangan. And that should be unrealistic, no? If we're going to take a look at that.